So welcome to the last week of Physics 30 content. Remember last week we left off with Bohr's model of the atom. So we have this positive nucleus thanks to Rutherford's gold foil. We have these electrons thanks to J.J. Thomson and his cathode rays. And we have these electrons in stable orbits, which can jump up or fall down and emit EMR according to Bohr's model. Now, Bohr's model of the atom did have several problems. Number one, why shouldn't electrons emit EMR when they are in their energy levels? They had some formulas that only worked for hydrogen. It found that the emission lines actually had a lot of smaller space lines, and some emission lines were brighter than others. So in Bohr's model, the electron was still considered to be a particle. It started to be clear, though, that electrons cannot just be thought of as particles. Maybe they're acting more like waves. So a lot of these scientists you'll see in this picture, this was a big conference where a lot of the famous scientists at the day got together, and they came up with a definition of quantum mechanics, quantum theory, and what it is that the body of science believed. Now, one big leap is the double slit experiment. We saw this before with light. Now, what's interesting is if we take electrons and shoot them at this screen with two slits, what we observe is an interference pattern. So if we shoot enough electrons at this screen, eventually we would have a pattern that would look like this. Now, this we know is an interference pattern, and from that we can infer that electrons are waves. We can infer that because our observation of an interference pattern is a very wave-like thing, which is weird because we're used to thinking about electrons as particles, when in fact they are waves. So what this means is that electrons aren't actually going through one slit or the other. An electron's actually going through both slits at the same time. And it's producing this interference pattern because they can actually be diffracted, and we see these areas of constructive and areas of destructive interference. The weird thing with this, and we're not going to get too much into it, is if we were to actually watch the electrons, so if we were to record which slit the electrons actually go through, that interference pattern actually disappears and they behave like particles, which is strange and maddening, and has to do with how measurement itself is not unobtrusive. By the fact that we measure things changes the properties of them. But yeah, if we were to record which slit they go through, we see particle behavior. But if we don't watch them, we see this interference pattern, which is wave-like behavior. Now, de Broglie kind of looked at waves. So he's like, okay, if waves could act like particles, then particles could also act like waves. And so this is the wave-particle duality. And he was able to relate wavelength to momentum. With this equation, momentum is equal to h over lambda. That means anything with momentum also has a wavelength. Now, things with a lot of mass have very small wavelengths. Like if you think about this equation, mv, so here's me moving at a certain speed is equal to h over lambda. If I think about the wavelength, so lambda is h over mv. So h is 6.63 times 10 to the negative 34. If I divide by my mass of 82, and my speed of like 10 meters per second, that's an immeasurable wavelength. Like it's like 10 to the negative 36 or 38. So that's not something that we would measure or be able to measure. Really small things traveling at high speeds do have noticeable wavelengths, however. If we think about this mass, like an electron, 10 to the negative 31, traveling at a speed like, I don't know, almost the speed of light, 10 to the 8. Now we're getting into things, still small wavelengths, but they're actually wavelengths that can be measured. So for an electron, so if we talk about kind of the Bohr energy model and why it works because electrons are not actually particles stuck in those rings. They're actually waves. So they're probability waves that are spread out. Electrons only exist in certain places because that is where those wavelengths are stable. If we think about them as standing waves, those standing waves are only stable at certain places. At other places, that standing wave breaks down. So that explains why an electron does not emit EMR and spiral into the nucleus following Maxwell's theory of EMR, because the electron actually exists as a standing wave, not a regular particle. We can't ask where is the electron. We can ask where is it likely to be found, but it is a probability. So this standing wave is the electron. So it's spread out in space. It's not just at one point. So the electron stops being a particle. Instead, the electron's mass and charge is thought of as being spread out in the standing wave. So it's everywhere as a wave. So even as a wave, the electron exists mostly near the Bohr orbit. So those orbits, those energy levels are places where that electron is most likely to be found. But again, that electron's spread out. So it's a probability distribution. If you think back to Chem 20 when you talked about orbitals, or if you did talk about orbitals, these orbitals, so if we think about the nucleus, right, we have different shapes. So if we have these orbitals around the nucleus, these are regions of space where the electron is likely to be found. It's like if you had information about me, like if you knew that I was at home sick, you could probably determine whereabouts in the house I would be, but not exactly where. So if I was at home sick, I'm probably more likely to be in the bedroom or the bathroom if I was throwing up. If I was hosting a party, then I'm probably more likely to be in the living room and kitchen and maybe on the deck. So based off of the information we have, we can get a probability distribution of where that electron will be. So the electrons have become a cloud of electrons, and we sometimes call this the electron cloud model. And that is our current model of the atoms. We have a positive nucleus surrounded by negative electrons, but these electrons are not particles, they're spread out as waves. Now we're going to go a little bit further because we haven't really talked too much about the nucleus yet. We're not going to have time to do radioactive decay, but we are going to talk about some of the smaller bits that make up matter, because physicists, they wanted to know, okay, what are the smallest fundamental particles that we know? Now this Dirac is another quantum physics guy. He predicted the existence of antimatter. So he thought that, okay, there must be this thing called antimatter. The models all predict it. What it is, if we take like a photon, so here's a photon, and it were to degrade in space, it would produce an electron, but there needs to be some form of conservation, right? We know charge needs to be conserved. We know momentum needs to be conserved. So if this photon, which has no charge, just energy, were to break down into an electron, there needs to be an opposite particle going in the opposite direction, and that's a positron. So Dirac, he predicted the existence of a positron. We sometimes call it an anti-electron. But it is kind of the first form of antimatter that we actually saw. We saw it by looking, they built these cloud chambers. So it's a vapor, supersaturated vapor that is just on the verge of turning into a liquid. And any disturbance, so any charged particle going through it will leave a track. And so when we look at the track that they leave, we see, oh yeah, there's this electron. If we have it in a magnetic field, we know using our hand rules that this one that goes up is an electron. Based off of the shape of the path of this bottom one, we know that it has the same momentum, so the same mass, the same velocity. However, because it goes the opposite direction, it must have the opposite charge. So I'm using my other hand. And that was kind of our first idea that, oh, antimatter exists. So antimatter has some interesting qualities. When matter and antimatter collide, it destroys itself and releases energy. So if we had an electron and it meets up with a positron, they will annihilate each other and release energy. You might have heard of Einstein's equation, E equals mc squared. It shows the conservation of mass and energy. So now we actually can create or destroy matter. It's just, it changes form though into energy. So the mass energy is conserved even though the matter maybe isn't there after this collision. So if we think about E equals mc squared, so we have each of these, an electron and a positron, has the same mass. So the amount of energy released in just one of these collisions is 2 times the mass of an electron slash positron times c squared. That would be the quantity of energy released in this collision. Now, so they saw this. So they saw antimatter, and from there, in the 1930s, physicists blew apart any possible way of going back to a simple model of matter just being made up of electrons, protons, and neutrons. They started to observe some of these particles that were very strange, and were not just protons, electrons, neutrons. So they started to observe things like muons and neutrinos, some different particles that they were detecting in some of these cloud chambers and other apparatuses. They also started to build these large particle accelerators. If we think about E equals mc squared, if we bring more energy into a collision, we have the ability to form more mass. The other reason why we need these large particle accelerators is that electromagnetic force is relatively strong. So if we have 2 protons being thrown at each other, we need to overcome that electromagnetic force in order for those protons to stick together and then break down into other things. But they were building greater and greater particle colliders all the way up to the LHC, which is what we currently have, over 1 tera electron volt. But they're colliding large energies together to produce these large masses. Okay, so, and when they did this, they started to absorb other particles as well. They also had natural particle accelerators in the form of cosmic rays, which were colliding with things in the atmosphere and then giving us some different particles. Now a muon, they noticed, acted like an electron but had a much greater mass. There must be an anti-muon, an antiparticle. They noticed things called pions, tau, all these other weird particles. And so they got to this subatomic zoo where instead of making things simpler, they ended up with over 300 fundamental particles, which was not a very simple model. To keep track, they divided these particles into groups based on properties like their interactions with other particles. So the 2 main groups were leptons, of which electrons are a part of. So electrons are an example of an lepton. You can't break down an electron any further. So an electron is a fundamental particle. Then there's these things called hadrons, which interact using the strong nuclear force. This is probably the first time we talked about this, but the strong nuclear force is the force that actually keeps the nucleus together. If we think about the nucleus, right, so here's just a helium nucleus. I have 2 protons, 2 neutrons. There's nothing really keeping these protons from flying apart, right? These protons are positively charged, and there's this strong electromagnetic repulsion that's actually trying to tear this atom apart. What holds them together is what's called the strong force. It's this glue which is actually responsible for a majority of the mass of the atom. But it's this strong force that acts only over short distances. So really only between nucleons. Over extremely small distances, it's actually a repulsive force, which is weird. but it holds that nucleus together. And it's also the reason why we have radioactive decay. So this strong force is holding the nucleus together. As nuclei get bigger, we have more and more protons, and the electromagnetic force goes up. So if the strong force is greater than the electromagnetic force, that atom is stable. But as these atoms get larger and larger, like for example, uranium-235, which has 92 protons now, now that strong force is not as strong compared to the electromagnetic force. And in order for this atom to reach stability, it'll decay. So it'll break down into smaller atoms, and that's what radioactive decay is. Give off alpha particles, for example. Now, so getting back to the strong force, that's what it is. Now, hadrons interact using the strong force, and we can break those down further into mesons and baryons based off their spin. So when we discuss the mass of all these fundamental particles, it is silly to use kilograms because that doesn't really make much sense in terms of the mass of an object. What we do use is a unit of mega electron volts per c squared. If you think of E equals mc squared, another way to express mass would be the energy of a particle divided by c squared. So that's another unit. We use mega electron volts, so 10 to the 6, because it just makes, if you look in this graph, it makes the numbers a lot easier. So for an example, like an electron, so an electron has a mass of 9.11 times 10 to the negative 31 kilograms. That's the mass of electrons. If we want to find the energy, so E equals mc squared. So the energy of that electron, let's get my calculator. So the mass of the electron, 9.11 times 10 to the negative 31 times 3 times 10 to the 8 squared. 8 so that's 8.19 times 10 to the negative 14. If I want to convert that into electron volts, so to do that I would divide by, so this is joules, I'd divide by 1.6 times 10 to the negative 19 joules. That's the amount of joules for 1 electron volt. And so I get 512,438 electron volts. And then as MeV, I'd move it 6 places to the left. I would have 0.52512 MeV. So that is the energy. And because we're really just c squared is always the same thing, I could write the mass as 0.512 MeV per c squared, and then that's a unit for mass. And so that's kind of where these values come from. It's just another way to communicate mass for particles like that. Now, by 1960s, physicists felt pretty confused. So they knew leptons are small, and there's only 6 of them, so it seems that they are probably fundamental. The hadrons are really big, and there's so many of them that maybe they were made up of smaller parts. And then in 1963, a couple of guys suggested that hadrons were in fact made up of things called quarks. So a proton is an example of one of these particles where a proton is made up of quarks. So a proton is not the smallest bit. A neutron is not the smallest bit. They're actually made up of quarks, and they're made up of combinations of up and down quarks. That's really the only quarks we need to know to make our model of the atom work. There are other quarks like charm quarks, strange quarks, top quarks, bottom quarks, and then all their anti-quarks as well. But in order to explain the nucleus, we really only need up and down. A proton has a +1 charge. Now an up quark is +2/3 and a down quark is -1/3. So in order to make a proton, we need 2 ups and a down. +2/3 +2/3 -1/3 gives us a proton with a +1 charge. In order to explain a neutron, we need an up and 2 downs. There's a form of decay called beta decay. So that's one form of radiation where an up is just changing into a down, and then it gives off radiation in that form. But that's really how we can model a proton and a neutron. Now, when we look at these, so these 3 quarks is how we explain a proton and a neutron. There are really way more quarks than that, and I would suggest you watch the Physics Girl video that's posted this week. It's a really good explanation of the quark model. So if you are confused, check that out. And there's also another video by CERN explaining the standard model, where it came from, also explaining some of the history like we talked about in the previous slide, that you should check out. But this is our model of the atom. That is our current model, is the standard model of the atom. We have these quarks, we have these leptons, of which the electron is part. And then we have these bosons, which are the force carriers. So the photon, which carries electromagnetism, the gluon, which carries the strong force, and then we have these Z bosons, Z boson, W boson, which are responsible for radioactive decay. And again, check out that CERN video, which is more of an explanation of the standard model. A lot of information this week. I know it's not super intuitive. The other videos I posted I think will help. And if you have any questions, feel free to ask. So this bothered physicists because it meant having charges that were a fraction of a charge, but then they actually saw the evidence of this. So that if you shoot electrons near a proton, near the up quarks, they actually bend more than near the down quarks, right? If we think of down quarks as -1/3, up quarks are +2/3. It's attracted to the up quark side and then slightly deflected from the down quark side. So with these 6 quarks and their antiquarks, we can explain all the hadrons. So all of the hadrons can be explained with these quark combinations. And that kind of